Hi, and welcome to the second part of Advanced Astrophysics Hertzsprung-Russell diagrams. We're really looking at stellar evolution here. We're looking at the death of stars in particular. Okay, there's a lot of words here. I wouldn't expect you to read through these. These are the SQA learning outcomes, or basically the course specification for this part of the course. Really, this is more like a set of notes. It's kind of the minimum amount you have to know. You don't have to know a huge amount more than this, though. You can do more reading if you want. There's plenty of stuff up in the Google Classroom for it, but this is the minimum amount. But the thing is, I'm going to go through all of this in the next few minutes. So this is the Hertzsprung-Russell diagram. Hopefully you should be familiar with this by now. The most important feature here is the main sequence. The main sequence is where stars are for most of their lives. So for about 90% of their lives, stars are going to be in this main sequence. Right, so what's important about this main sequence? Well, it can contain lots of most of the stars in the universe are basically in the main sequence. The stars can be small and slightly cooler, redder stars, or they can be bigger and much hotter, bluer stars. This makes quite a lot of difference to their lifetime, but it also makes a lot of difference as to where they'll end up at the end. We're going to have a look at that in a wee second, whether they form giants, supergiants, and then eventually white dwarfs, or what happens to them after that. That's basically the point of this lesson. The most important feature of the stars in the main sequence, though, is that they are all fusing hydrogen. So this reaction on this side here, where basically hydrogen is being fused, or most of it where hydrogen is being fused to form helium, this is basically what's happening inside a main sequence star. And it's happening inside all the main sequence stars, the big ones and the smaller ones. Right, the next part of what we're looking at is going to be to look at what happens to the main sequence stars. Before we come off this, the most important determinant or the only determinant of what's going to happen to a main sequence star is actually its mass. So the stars down here, around about where the sun is, and a bit smaller and a little bit bigger, up to about 4 times as massive as our sun, will basically become giants. Anything bigger than that will become supergiants, and they have different life cycles. But remember that the main sequence is 90% of their life. The rest of their life is in terms of formation of the star, and then in terms of what happens to it afterwards. So, for main sequence stars, where, again, to reiterate it, most stars are for most of their lives, the gravitational force pulling inwards is balanced by the thermal pressure pushing out the way. And the thermal pressure is caused by fusion, which is really only taking place in the core of the star. So that hydrogen fusion is really happening in the core of the star. And that's probably the most important thing to take on board here. Main sequence means that hydrogen fusion is happening in the core. There's hydrogen out here too, but it's not fusing at this stage. Okay, the thermal pressure from the hydrogen fusion in this core is pushing out the way. It's been balanced by the gravitational force. Not much changes. For 90% of the star's life, you've got basically the same process. The star is pretty much the same size, and everything goes on as it is. But then eventually, the hydrogen is going to run out, or the hydrogen in the core, is going to. So what happens when the hydrogen in the core is depleted or runs out? Well, we've got a nuclear reaction happening here in the core of the star. We've got a fusion reaction, but it's going from hydrogen to helium. So when the hydrogen's gone, then this reaction in the core effectively ceases. As this reaction in the core ceases, the thermal pressure in the core starts to reduce, and what happens is that the entire star basically starts to be pulled in the way. The gravitational forces can no longer be resisted by the thermal pressure. Remember, the core is at the moment made up mainly of helium, because the hydrogen's pretty much all been fused into helium, or a majority of it has. And so what happens is the outer shell of the star that contains hydrogen here starts to actually compress in the way too. So as it's compressing, this gas in the outer shell is starting to heat up. And it's starting to get the ions of hydrogen are starting to get pushed closer and closer together. And eventually what happens is that the temperature of the hydrogen here and the extreme pressures actually cause nuclear fusion to start up again. Right, so what we've got now is we've got a situation where the hydrogen in the shell of the star has actually now compressed enough that it can start fusing together again. So we've got nuclear fusion now happening within the hydrogen in the shell, and the core has got helium in it. And the helium in the core has now actually started to fuse together too. How has that happened? Well, because the temperature of the core as it basically compresses, and the pressures in the core are much higher. So the temperatures and the pressures have basically increased an enormous amount, and what that's done is it's allowed the helium atoms to actually, the helium ions, I should say, to fuse together to produce some of the larger mass elements, so things like carbon and oxygen. So some of these heavier elements are now being produced in here, and also a lot of heat's being produced in here. We're back to nuclear fusion happening here. We've got nuclear fusion happening in the shell too. And so what that does is actually has the effect of now pushing the shell outwards. The core basically still stays quite compact, but the shell of the star expands outwards enormously. In fact, the shell of the star expands to the size, well, for a star like the Sun, to the size that it would actually engulf Mercury and Venus, and would actually come pretty close to Earth as well. I mean, this is a massive expansion, and this is what will happen to our Sun in a few billion years. Our Sun's kind of middle-aged in terms of a star life. So basically, as the star expands, we've still got a huge amount of energy being produced, but because it's being produced and being spread out over a much larger surface area, or it's been given out over a much larger surface area, the temperature, in particular the surface, the temperature basically is reduced, and that's why this star is a red star. If this happened with a star about the size of our Sun, or thereabouts, then a little bit bigger, a little bit smaller, well, it will produce a giant, a red giant. If it happens in a much larger star, then it will become a supergiant star, depending on its mass. So, we're back to this again. So, the main sequence is what we've kind of described there at the beginning, when we get hydrogen fusion. Once the stars actually start, the hydrogen runs out, then the stars basically make their way up to either become giants or supergiants. Now, I'm simplifying a little bit, but as far as we're concerned, a star around about the mass of our Sun, more or less, a little bit bigger, a little bit smaller, will, or a fair bit smaller, will actually become a red giant. The bigger stars will become a supergiant. There are various other stages in between in terms of what they do, but we're not really going to look at that. But that's not the final fate of these stars. The final fate of the stars depends very much on the mass of the stars. Our Sun, for instance, will become a red giant, and then eventually that red giant will, or the core of the star will basically stay hot, and it will throw off its atmosphere effectively. It will throw off all the outer gas, and it will actually cool down to form a white dwarf. If you want more information on that, follow the video links that I've given you in the Google Classroom. Some of the larger stars, though, have a slightly different lifespan, or life cycle. I'm going to restrict myself on this just to talking about a summary of what's going on here. Please go to the video links from the Google Classroom, which will give you much more detail about any stage in this process if you're interested. The bits that we really need to know about are that stars are basically formed from molecular cloud when gas and dust are compressed, or gravitational forces pull them together, they compress, they heat up, and eventually you get to the point where hydrogen starts to fuse and you form a star. The stars that we are really interested in here are stars that are around about the mass of our Sun. They're called low mass stars, low to medium mass stars, and a little bit with massive stars up here, which are much bigger than our Sun. So a low mass star like our Sun, or a medium mass star like our Sun, will basically form a red giant. We just talked about that. We're not going to worry about what's going on up here. We're just going to look at what happens to the majority of them. The majority of them, the red giant will eventually throw off its outer shell, and it will form what's called a planetary nebula. Planetary nebula is not actually anything to do with the planet. It's a historical inaccuracy, effectively, but the names kind of kept going. These don't form planets. In the middle of this, though, we'll be left with a white dwarf. The name kind of tells you a lot about it. It's white because it's actually still very, very hot, very, very dense, and it's actually very, very small. And white dwarfs, really, for their lifetime, eventually, over many billions of years, or millions of billions of years, will actually cool down to eventually form black dwarfs. So they get dimmer and dimmer over a long, long period of time. It's a bit more exciting, though, if you have a massive star. If you have a really, really massive star, you still go to a red giant stage. We call this a red supergiant, but it's a similar process. But what happens to a red supergiant is that it basically, at the end of its life, it's got enough mass that it actually causes one of the biggest explosions, or the biggest explosions in the universe, where for a very, very brief time, and it really is a brief time, you can sometimes see them in the sky, but they might not last longer than a few minutes or a couple of hours, that you get what's called a supernova. A supernova is a massive explosion where some of the heavier elements or all of the heavier elements, all the elements heavier than iron, certainly, in the universe, are basically created. The heavier elements are created in these supernova, and that's the only place you can get them. Because we have these heavy elements here on Earth, then we know that certainly they must have been produced in supernova explosions. And so definitely, a lot of the world, or some of the world around us certainly, has come from a supernova explosion, or the remnants of a supernova explosion that's formed planets in a new solar system. If the star is greater, or less than 40 times the mass of our sun, then it will eventually form what's called a neutron star. Now again, I don't want to go into too much detail here, but a neutron star is a star that where effectively electrons and protons have been squished together to form neutrons, and it's only the pressure of neutrons themselves. I mean, this is basically where atoms have been effectively squished out of existence. It's called, it's to do with electron degeneracy, effectively the fact that electrons normally can't overlap, so you can't have two atoms like virtually on top of each other. But once the gravitational field strength, as it does here, gets big enough, then that can happen, and eventually you end up with this massively it's massive in the sense that it's got huge mass, but the massively dense neutron star here, where effectively I think the statistic is normally 1 teaspoonful would weigh the same as the entire human population. We're not going to go into pulsars at the moment, but if it's bigger than 40 times the mass of the sun, then it actually, when it collapses down, instead of going to a neutron star, it actually has enough mass, the gravitational forces are so great that it actually keeps collapsing down until eventually it gets to singularity, virtually nothing. The gravitational field strength gets so great that even light itself cannot escape, and you get a black hole. Okay, that's as far as I'm going to go for here. Have a look though at some of the other videos that I've linked to in the Google Classroom to get more information.